Hello and welcome. My name is Spencer and this is Orpheus. Couple things I want you to keep in mind while you're watching. This is a research project, so there won't be any fancy GUIs or interfaces of any kind. It'll be pretty bare bones, but it'll be super interesting if you like deep learning. The idea for this project was born from me trying to create an intrusion detection system and realizing that finding good data sets for that is nearly impossible. You need high quality network data and network traces to train the intrusion detection systems, and a lot of this data that would be of good quality in companies and stuff like that is all privileged information because these packets contain tons of confidential information. So companies don't really want to release these data sets because they can't. So a lot of the public data sets are super heavily anonymized by stripping out important information like IP addresses, the payload. It makes them really low quality for learning algorithms. So throughout this presentation, you're going to see me try to modify a convolutional neural network based generative adversarial network, which is normally used to generate images, and I'm going to modify it to generate realistic network packets. And if I can improve this model enough, eventually researchers could use it to anonymize network data sets from large companies, which would preserve the quality of the data while removing any of the privacy concerns they had. So as I mentioned before, I'm going to use a GAN to try and achieve this, and I'm just going to give you a little bit of a background on what a GAN actually is. So it consists of two neural networks, a discriminator and a generator. The generator is trained to reproduce new data that's indistinguishable from the real data, where the discriminator is trained to classify if its input data is real data or fake data. So they kind of work in like a mini-max game where one is maximizing the objective function and the other one is minimizing it. Basically, the generator generates new packets, like fake ones, and then gives those to the discriminator, and we also give the discriminator real data, and then the discriminator tries to tell the difference between the two, and if it can tell the difference between the two, then the generator hasn't done a good enough job, and it feeds that loss back into the generator takes that as input, and then tries to make better packets that can fool the discriminator. So as I said before, GAN is just kind of a training architecture. It needs an underlying neural network that it's based off of. So this one is based off of convolutional neural net, which was originally designed for image classification. It's got many layers where the early layers detect simple patterns and the later layers recombine them to make predictions about what that image is. The discriminator will just be a regular CNN that would be used for supervised classification. It's not going to be anything complicated. Since it's just used for training, we're just going to throw it away after and just keep the generator at the end of this. The generator. This is the really important part of the GAN. So the generator is basically just a convolutional neural net that's flipped around backwards. So instead of taking in images and giving predictions, it takes in a noise vector, which is just randomly sampled points from a normal distribution, and it outputs grayscale images, which in our case is just matrices of byte values, and that can be decoded back into network packet bytes. Normally in these matrices, each one of those byte values in each of the matrix squares would represent a pixel, but in our case it's just going to represent one of the byte values of the network packet. So this is just a little bit of an overview of how the whole process goes. I'm going to get into much more detail on each of these steps, but the basics are you collect data, which in my case is from Wireshark on my home network. You pre-process that data to turn it into an image representation. You then train the GAN. And once you're done training the GAN, you take the generator, you generate a small data set. You have to then decode these samples out of their image representation back into their packet byte value representation. And then you have to verify the model's actually doing what it's supposed to using performance metrics. In our case, that'll be the number of packets generated successfully divided by the total number of packets generated. And as you can see down in the picture, you can just see a little pictorial representation of how this stuff works and how the GAN output looks as a 28 by 28 grayscale image. So to keep the scope of this project reasonable and able to be done within the time allotted, I chose to just stick with creating DNS query packets. So during the data collection, I just put Wireshark on my computer, filtered for DNS queries. I also collected a small amount of ping traffic using a script just to ping popular websites. I'll talk about that later and how it improved the GAN's performance. So after several days of collecting data, I ended up with about 47,000 DNS packets and about 1,000 ICMP ping packets. So you can see a sample DNS packet as a byte stream. So it consists of 4 parts. The first part is the Ethernet header. We don't need that, so we just throw that away. The other 3 parts are the IP header, the UDP header, and finally the DNS packet. And on the bottom of the slide, you can see all the different byte fields that have to be correctly generated by the generator in order for the packet to be successfully sent through the network. So as I said before, these CNN GANs are normally used for images, but we're going to use them for packets. So in order to do that, we have to pre-process the packets. So at its core, like, an image is basically just a matrix of pixel values, right? So in this case, maybe a 28 by 28 matrix, and each spot in that matrix is just a value of an RBG value of a pixel. So what we're basically going to do is we're going to take those byte values, we're going to map them onto a 28 by 28 matrix so that it can be used like an image. And that takes 2 steps. We're going to have to do the packet byte value conversion in the first step, and in the second step, we're going to do the packet byte value 1 to multi-mapping. Now you might ask, why not just map each byte value to one spot on the matrix, like a pixel? Well, the problem with that is CNNs are meant for images where they have tons of pixels, and if there's some slight variation in the recreated image, you probably won't see it with the human eye. However, if there's a problem with one of the byte fields, then the network is definitely going to notice because of how strict packet formats are. Like, if even one is slightly off, then it won't be able to be sent through the network. So to avoid this problem, we have the packet byte value conversion, which basically takes the byte values and then creates a sub-range of values. And then we take that sub-range of values and we map it multiple times onto the matrix. So when the CNN kernel looks at it, it has a range of values that basically act as error margins. So when we re-average those values, we get back a value that's within spec. So as I said, each byte is going to end up being broken down into a sub-range. So this is like a little example of what you would do with the byte 1F. So like, first, the hexadecimal digits of each packet byte are separated. So you would take the 1 and the F. The digit 1 would be represented by the range 10 to 1F, and the digit F would be represented by the range F0 to FF. Then the final values assigned to the matrix are 18 and F8. I'm going to try to keep the math in this video to a minimal, but I do encourage you to pause the video and see if the math checks out. The second step is the packet byte 1 to multi-mapping. So in this step, the converted byte values are duplicated multiple times and mapped onto the CNN matrix. It's necessary so the CNN can learn to exploit the positional properties of clusters of similarly converted byte digit values. So on the right, you can see the pseudocode for it. I'm not going to explain it, but if you want to go through it, it's there for you. The second image you see there is it actually being mapped multiple times onto the matrix. So as I mentioned earlier in this presentation, GAN training, the discriminator and generator are trained in step with one another, but with opposing objective and loss functions. So what that means is that once the generator generates a packet from the noise vector, which can be from a normal or a uniform distribution. I used normal, but you could have used uniform as well. The discriminator is fed the fake data and the real data, and it tries to tell the difference. And once it outputs its loss, both the discriminator and the generator are updated from this loss at the same time. However, one minor difference with the GAN that I'm using is that the discriminator actually does 5 training steps for every 1 step of the generator. Now that's just a hyperparameter that I tuned and found that it worked really well. So the loss function I ended up using was the Wasserstein loss, I think that's how you pronounce it, which is also called the earth mover distance. And what it's defined as is the average distance required to move the probability mass from one distribution to another. So in our case, move Q, which is the generated distribution, to P, the real distribution. In regular GANs, the discriminator's loss is the probability that the input is fake. So the output function is sigmoid, and it outputs on a scale of 0 to 1, which doesn't have a really big range of values. Now with the Wasserstein loss, the discriminator now outputs on the scale of -1 to 1, and it can use tan h as its output function. It increases the gap between the scores for real and fake images. It also scores it based on how real an image is, rather than if it's actually tricking the discriminator. So large positive losses for the discriminator means that the generated images are passing as real images, and a large negative loss means the generated images are poor quality. So now that we're done with all that background, this is a full picture of how the GAN is designed. So what it is called is WGAN-GP, which stands for Wasserstein GAN with gradient penalty. So it's a relatively new architecture, it just came out at the start of 2018, and it introduces a gradient penalty term to enforce the one Lipschitz constraint on the Wasserstein loss function. I'm not really going to explain all the math, but if you want to read more about it, it's the second citation at the end of this presentation. So basically you have three images, a real one, a fake one, and an interpolated one. So you can see that as R image is the real one, A image is the interpolated one, and F image is the fake one. So the interpolated image is created by taking a matrix of epsilon values, which is basically just weights randomly sampled from a uniform distribution. You then merge the real and fake images together according to the matrix of weights. So if the first value in the matrix is 0.8 as epsilon, you get 80% of the real image's first pixel and 20% of the generated image's first pixel, or in our case, the packet byte values. These three images are then fed into the discriminator, and a loss value is calculated for each. So the interpolated image is for the gradient penalty term. The real image gives the real image loss, and the fake image made by the generator from the input noise vector is for the gradient loss. So the discriminator loss is the loss on the fake image minus the loss on the real image plus the penalty term. But the thing that's really important is the gradient loss, which is the negative of the discriminator loss. So what that means is if the discriminator outputs a large loss value, meaning the fake images are looking realistic, then the negative of that is given to the generator, resulting in a super small loss for the generator, so it knows it's doing well. This process repeats over and over and over again until they converge. So until the discriminator can no longer tell the difference between the real and the fake images, and the fake images have the same quality as the real image in theory. So here you see the discriminator's loss graph. On the side you see it called critic. Critic discriminator means the same thing. So the blue is the critic's loss on generated images, and the red is the critic's loss on real images. And where I have circled in green around epoch 4000, you can see a really interesting spot in the training. So loss on the generated images becomes very negative. That means the discriminator is correctly classifying this fake. However, this is good because, as you can see, after it dips down, it sharply starts going up until it passes the red line and is above, which means the discriminator is classifying the fake images as real. This behavior can be explained as two networks working how they're supposed to in unison. The discriminator loss on fake images drops, meaning it classifies them as fake. It is feeding this valuable loss data back into the generator, which learns from it and generates much better images very quickly until they become good enough the discriminator thinks they are real, at which point the value in the loss data isn't as good and the critic learns new ways to tell the images apart. And once it does, the loss drops again and the cycle repeats until eventually you stop training at a point where the generator is good enough and further training will just be detrimental. So because as I said at the beginning, I don't have any fancy GUIs or anything to show you, I figured I'd just show you a little bit of what the model architecture is and what it looks like while it's training. So first, the critic consists of 5 layers. It's got 4 2D convolutional layers that each have a kernel size of 4 and stride 2. And then it's got a flattening layer and a dense layer at the end for the final classification. The generator consists of 7 layers. The first 3 are fully connected layers that take an input noise vector of size 64, and then an output vector comes out of that layer of size 12544. The reshape layer is then used to form 256 instances of 7x7 square matrices. And I got 2 deconvolution layers. They're applied to upsample these matrices to size 14x14, and then 32 instances of the desired 28x28 output size. A final convolutional layer is used to produce a single instance of the packet in encoded matrix form. Over here, this is what training looks like. So every 100 epochs, it prints out an example packet, so I just kind of know what's going on and know if it's training properly. It also prints out the discriminator loss and the generator loss every 25 epochs. So if you can see here, the first one really makes no sense. IP version 7 doesn't exist, doesn't really know what it's doing, doesn't know what it's creating. This is what the DNS string looks like, just a bunch of 7s and 8s, because it really hasn't learned anything yet. After about 100 epochs, it's starting to learn some stuff. The IP version is 4, which is good, that's correct. The flags, 1, that's pretty common. Protocol 0 doesn't exist, so that doesn't really know. The DNS is malformed, but the DNS string is starting to look like something else other than just some random gibberish. As we go down, you can start to see the string getting more refined. The zeros at the end are just because the DNS packets don't fill the full 28x28 square matrix usually. It just depends on the size based on how big the name is that we are querying. And then if we go down, we can start to see the graphs. So at the beginning, obviously, there's nothing, and then you can see here the critic loss curves and as they change. And this is really all I have to go on when I'm trying to figure out what's going on during training. So yeah, it's not a lot. You just kind of gotta look and figure it out. And eventually, it'll get to a point where it starts generating packets that do in fact have correct DNS information, and we'll see that later. Okay, so now training is finished, and got some pretty good results. You can see here, IP version's correct, total length, blah blah. The offset I just set to 0, and same with the checksum, because it's going to be pretty impossible for them to calculate those values properly. It doesn't say here, but I have set it to 0 just so it can properly form the DNS query packets. So you'll see here a bunch of properly generated packets. The fields are making more sense. IP addresses look good. Source and destination ports look good. The checksums and the lengths, I'm not gonna end up doing, because there's no way it's gonna generate those correctly every time. So let's see, as we go down, generated about 100 of these packets just to check what our accuracy is like. So our generation success for this run, about 80%. So I'd say that's pretty good. If we run this again, we'll see generation success about 79%. So we're in about the 80% range. See again, 82%. Let's see if we can get something a bit higher, 69. So yeah, then it drops down sometimes. Sometimes it's up, sometimes it's down. This one looks better, 77. Yeah, so we're about 75 to 80% accuracy range, which is pretty good. And here you can just see what I'm literally doing to print out these packets for you. So I literally just take the DNS string, like the raw string that comes out after it's decoded, and then I just have to take it apart, byte value by byte value by byte value by byte value, and put them all together and then give them some labels so it kind of makes some sense. Down here you can see the input noise vector. For whatever reason, I'm actually not sure why, but when you're generating packets, it's better to use a uniform distribution, whereas during training it's better to use a normal distribution. I just got that from parameter tuning. So these are the hyperparameters that I ended up using after quite a lot of tuning. So gradient penalty is equal to 10. The layer-wise L2 regularization is 2.5 times 10 to the minus 5. So I ended up using layer-wise L2 regularization instead of batch norm because that just worked much better for the GAN. Number of critic steps per generation step is 5, so the number of steps, training steps, the critic takes for every generator step. The ping packet inclusion was 2% of the packets were ping packets. That actually helped quite a bit to stop overfitting. I'm pretty sure because they have common IP headers. The batch size is 32. Epochs took anywhere from 17,500 to 18,000, but more than that, and the overfitting got pretty bad and it just didn't work. On the Atoms optimizer, the learning rate was 0.001 with a beta 1 of 0.5 and a beta 2 of 0.99. So as you just saw, once training's finished, we generate samples, but somewhere in the middle of that, after the samples are generated, they have to be decoded from their image matrix representation back into packet form, and that's what this formula here does. So if you look at the red square in the matrix, the first thing we would do is average those 4 values. So the average of the 4 18s is 18. And then we would average the green square next to it, which would be F8. Then if we go back to looking at the value 18, we would split it into its components, 1 and 8, and then put it through the formula. And I did the example right there, you can read it for yourself, but as you can see, the recovered byte value is 1F, which is the same value that we put into the encoding step earlier in the presentation. And I encourage you to pause the presentation and look back to make sure that they are in fact the same value. So the last step is to verify that the model's actually working correctly. And as you saw in the little demo I did, I just kind of used a DNS packet parser that I installed as a Python package to verify that they were in fact generated correctly. Malformed packets would generate an error message explaining what part was malformed. And most of the time the part that was malformed was just the DNS string itself, like the web address, because the generator just wasn't doing a very good job of putting that back together. But in the end, the performance metric would be the success rate, which is defined as the number of successful generated packets divided by the total number of samples generated. And last but not least, the results. So my best model, the success rates are around 75 to 80%, which I'm pretty happy with. One of the challenges I had with this was the model overfit a lot. And I'm thinking that's probably just because I needed a lot more data to train this. GANs are very data hungry. And I think I just needed them from a wider variety of sources because all the DNS data and ICMP data was coming from my computer, so a very limited range of IP addresses and such. Adding a small amount of ICMP packets did reduce the overfitting problem. I'm assuming it's just because they had a common IP header, so it allowed it to get a little bit of variety in the data, which just reinforces my last point. I also think the model could have much better success rates if I had more time for hyperparameter tuning, but each training run was anywhere from 3 to 5 hours, so it was pretty hard to tune those parameters effectively. And finally, one thing that was actually kind of cool was even though I generated the checksum fields myself, even when I didn't, it still managed about a 10% success rate, which I think is pretty amazing because those checksum fields are pretty tricky. So thank you for sitting through this presentation with me, and I hope you learned something or enjoyed it. The references are on the last slide, and those are the 3 papers that I use most to kind of design this thing and make it work. So yeah, thank you.